Hello everyone. The topic is linear delay model. So first let us consider an inverter. This is sized as 2:1. So of course this is a PMOS on the top here. So assuming the sizing is based on the assumption mu P is equal to half mu N, so that the charging current is equal to the discharging current. So now we know that the discharge current is proportional to mu n C ox W by L, right? Mu n C ox and W by L is 1 in this case for NMOS. And I charge is proportional to mu P C ox W by L. W by L is 2 in this case. And mu P is nothing but half mu N. Therefore, this is equal to mu N C ox, which is the same as that of the discharge current. So we can say that here the charging current is equal to the discharging current of the inverter. Also here we can say that the resistance of any transistor, let's say NMOS, is proportional to 1 by mu N C ox W by L. The resistance of the PMOS is proportional to 1 by mu P C ox W by L. Since W by L of NMOS is 1 and W by L of PMOS is 2 and mu P is equal to half mu N, so R of NMOS is equal to R of PMOS. Okay, now for simplicity, let's consider L is equal to 1. The capacitance at the output node is directly proportional to C ox, that is a unit capacitance, the oxide capacitance per unit area into W, which means the capacitance offered by both the transistor is directly proportional to its width, right? Therefore, we can say that the delay, the charging and the discharging delay of this unit inverter is directly proportional to the delay. Charging and the discharging delay of the inverter is directly proportional to the resistance offered by it as well as the capacitor. So now here, let's just redraw this unit inverter again. So each of this offers a resistance equal to R, and the PMOS has a width of 2. Therefore, due to this PMOS, we'll have a capacitance 2C at the output, and due to this NMOS, we'll have a capacitance C at the output. Therefore, the total capacitance at the output will now be equal to 3C. 2C due to the NMOS and 2C due to the PMOS and C due to the NMOS. So now the charging delay, that is delay charging, will now be equal to, we can write it in terms of RC constant, that's due to the PMOS, which offers a resistance of R, okay, and then the effective capacitance here is 3C. So therefore 3RC is the charging delay, and the discharge delay that is through the NMOS, is again equal to R, that is the resistance offered by the NMOS, into the output capacitance, that is 3C, which is again equal to 3RC. So now I have an inverter here. What if I cascade this inverter with another inverter? Now this is my input, this is an intermediate node X, and this is the output. So now we'll have to calculate the charging and the discharging times, the charging and the discharging times at X, right? So what do we do? So we have an inverter here. Okay, we in. We have another inverter here. Okay, so the output of this is given as the input to the next inverter, and here is the output, and then this is the node X, and let's size it similar to an unit inverter. Okay, so this is 2, this is 1, and this is 2, and this is 1, right? Therefore the total capacitance here will be 2C due to this, C due to this NMOS, 2C due to this, and C due to this NMOS again. Therefore the total capacitance here will be 6C. So now in this case, delay due to charging will be the resistance offered by the PMOS into the effective capacitance at the output X, which is 6C. Now here I am talking about the charging and the discharge delay at this point, right? Similarly, the delay due to discharging is also equal to 6RC. So now if I have to normalize this with respect to the delay of an unit inverter, then I divide both of this by 3C, and then I can say delay of an inverter that is cascaded to another inverter, that is the delay at this point, is equal to 2. That is, I am normalizing this delay with respect to an unit inverter, right? So the delay is 2. Now let's take the example of a 2-input NAND gate. Okay, so here you have two PMOS in parallel, and then you have these two NMOS in series. This is A and this is B, this is A and this is B. So now we'll have to size these transistors, the NMOS and the PMOS, such that the resistance of each of these branches during the worst case charging and discharging times is equal to R. So in case of the PMOS, the worst case will be when any one of these transistors is on. Therefore, in order to get the resistance equal to R, we size both these transistors equal to 2. So the worst case discharge is when both these NMOS transistors are on. So this whole path should provide us with a resistance equal to R, so that we'll have equal charge and discharge currents. So for that reason, we size these NMOS transistors so that each of them will provide us with a resistance equal to R by 2 and R by 2, so that the total resistance is R, right? So therefore, the size of these transistors is also equal to 2 and 2. So in the linear delay model, we consider the delay only with respect to the output capacitance and not the intermediate diffusion capacitance, right? So now, what will be the output capacitance? The output capacitance here. So this total capacitance will be, the contributions are like this. So that is, you will have 2C because of this PMOS, 2C because of this PMOS, and 2C because of this NMOS. So the total output capacitance here is equal to 6C. So now the charging delay is equal to R times the output capacitance, which is 6C, and the discharge delay is also equal to 6RC. So now what happens if we cascade this 2-input NAND gate with another 2-input NAND gate? As in, it looks something like this. You have a 2-input NAND gate here. So now you cascade another 2-input NAND gate. So as you can see here, the input capacitance here will be equal to 4C. The contribution from the NMOS here will be 2C, and the contribution from the PMOS here will be 2C. Therefore, the effective capacitance at this point will be 4C. So that is the input capacitance of a 2-input NAND gate. So when you cascade 2 gates like this, then at this point, what is the total capacitance? With this, will have a total capacitance of, first it will have a capacitance of 6C, which is the output capacitance, of this NAND gate, and then this will have another capacitance due to the input of this NAND gate, so which is 4C as we saw here. So therefore, this will have another capacitance which is 4C. So the effective capacitance at this point, cap effective, now is equal to 10C. So let me call this point as X. So now, in order to charge or discharge a capacitor at node X, so the delay due to charging is equal to R times 10C. Similarly, the delay due to discharging is also equal to 10 times RC. Now, if I have to normalize this delay, with respect to unit inverter, then I divide 10 RC by 3 RC, which is the delay of the unit inverter, and therefore I can write this as 10 by 3. This further I can write it as 2 plus 4 by 3 into 1. Let's see why we wrote like this in some time. Now let's consider a 2-input NOR gate. Okay, so the 2-input NOR gate looks like this. You have PMOS in series, then NMOS in parallel. Right, so this is A, this is B, here this is A, and this is B, and this is the output Y. So here we size the transistors again such that we have worst case equal charge and discharge currents. So now the worst case on the NMOS side will be when one of these two transistors is on. As in, when one of these two transistors is on, this should provide a resistance equal to R. Similarly, here when both the PMOS transistors are on, this should provide a resistance equal to R. As in, each of these transistors must provide a resistance equal to R by 2 and R by 2. So therefore, we will have the sizing of the resistors with respect to the charging and the discharging currents. It's 1, 1. So a PMOS with a size 2 provides a resistance R, and a PMOS with a size 4 provides a resistance R by 2. So at the output now, the capacitance will be equal to 4C, 4C due to this PMOS, C due to these two NMOSes, which is nothing but 6C, right? And therefore, the delay due to charging will now be equal to R times 6C, and the delay due to discharging will now be equal to 6RC again. Now let's take a look at the input capacitors. So the input capacitors are nothing but the input gate capacitors. So therefore the capacitor at this point will be 5C, right? That is C due to the NMOS and 4C due to the PMOS, which is 5C. Now let's see what happens if we cascade a NOR gate with another NOR gate, and let's to find out what are the charge and the discharge times at this point. So as you can see, this will have a capacitance of 6C, as we see here, due to the output capacitance of the first gate, and the input capacitance of the second gate contributes a capacitance of 5C, as we see here, right? Therefore you will have another 5C here, and therefore cap effective now at that point is equal to 11C. So now I can say the delay, that is charging delay at the point X here, will be equal to R times 11C, and the delay discharge will be equal to R times 11C, the normalized delay, that is the normalized delay with respect to unit inverter is now equal to 11 by 3. Now this 11 by 3 can be written as 2 plus 5 by 3 into 1. Now for an inverter, we saw that the delay, normalized delay, was equal to 2 when one inverter was cascaded with another inverter. This can be written as 1 plus 1.1. So in the case of a NAND gate, when one 2-input NAND gate is cascaded with another 2-input NAND gate, we saw that the normalized delay was 10 by 3, which can be written as 2 plus 4 by 3 into 1. And in case of a 2-input NOR gate, the delay was 11 by 3, which we wrote it as 2 plus 5 by 3 into 1. So we can generalize this, okay? So any delay, normalized delay, can be represented as P plus GH, where P is the parasitic delay, G is the logical effort, and H is the electrical effort. So the definition of this is as follows. Parasitic delay is nothing but the output capacitance, parasitic capacitance of the gate under consideration, divided by the output parasitic capacitance of unit inverter. This is the output capacitance of the gate under consideration, right? Okay. Now next, the logical effort G is the input gate capacitance of the gate under consideration, as in gate under consideration. This refers to the gate of a MOSFET. This refers to the NAND NOR AND gates. Okay, divided by input capacitance or input gate capacitance of unit inverter. Okay, H here is nothing but the fan out. Okay, H is the input capacitance of load divided by the input capacitance of gate under consideration. So now let's take a look at the examples that we have written above. So P of an inverter is the output parasitic capacitance of the inverter divided by the output parasitic capacitance of the unit inverter, which is 1 in this case, 3RC by 3RC. Similarly, if you go by the definition, so parasitic capacitance P of the unit inverter is equal to 1, because the definition says the output capacitance of the gate under consideration. The gate under consideration is here is nothing but unit inverter. So therefore the ratio gives you 1. Similarly, the input gate capacitance of the gate under consideration is again in unit inverter. Therefore the ratio gives you 1. So now if we have two similar gates cascaded, then the input capacitance of the load will be equal to the input capacitance of the load under consideration. Therefore, this again the ratio gives 1. Therefore, we can write the delay of the inverter is 2. Similarly, look at this NAND gate. For a NAND gate, the output capacitance, parasitic capacitance of the NAND gate divided by the output parasitic capacitance of the unit inverter. So this was equal to 6 in case of NAND, and this is equal to 3. Therefore, the ratio gives 2. So parasitic delay of the NAND gate is 2. So as per this definition, the input gate capacitance of the NAND gate is 4. The input gate capacitance of the unit inverter is 3. Therefore, the logical effort is 4 by 3. And since we are cascading two similar gates, H, the electrical effort is equal to 1. Similarly, in case of a NOR gate, so for parasitic delay, the numerator is 6, the denominator is 3. Here in this case, the numerator is 5, that is the input capacitance, gate capacitance of the gate under consideration, that's 5, and this is 3. Therefore, we have 5 by 3, and the electrical effort H is equal to 1. Now, let's cascade a 2-input NAND gate with a 2-input NOR gate. Right? So now, what is the effective capacitance at this point? So the output capacitance of the 2-input NAND gate is 6C. The input capacitance of the 2-input NOR gate is 5C. Therefore, cap effective at this point X, is equal to 11C. So we can write the delay while charging the capacitor at node X is equal to 11 RC, and that's equal to the delay while discharging. So this can be again expressed as D is equal to P plus G H. So what's the parasitic delay of a 2-input NAND gate? We have seen that's equal to 2, right? Plus What is the logical effort of a 2-input NAND gate? It is the input capacitance of the 2-input NAND gate divided by the input capacitance of a unit inverter. And what's H? H is equal to the input capacitance of the load. Load here is the 2-input NOR gate. Load for the 2-input NAND gate here is nothing but the 2-input NOR gate divided by the input capacitance of the gate under consideration, which is the 2-input NAND gate here. So that is the input capacitance of that is 4. So this is nothing but 2 plus 5 by 3, that is 11 by 3. As you can see, if we normalize this delay that we calculated here, delay normalized with respect to unit inverter is nothing but 11 by 3. So therefore we can calculate the normalized delay of any circuit or any point using this equation, which is normalized delay D of a gate is equal to its parasitic delay plus logical effort into the electrical effort.